You sit down for the Math 260 midterm, flip to page 2, and your brain immediately defaults to panic mode. Look at this question from a past exam. It's a parametric linear system, and the professor buried an algebraic variable, in this case a, right in the middle of the equations. The design is intentional. If you try to isolate variables through standard substitution, you will run out of time. Then there is this problem, finding the determinant of an adjoint matrix. Manually calculating the full adjoint of a 3x3 matrix involves finding 9 separate cofactors. Doing that by hand under exam conditions is a guaranteed way to exhaust the clock. Success on this midterm relies on recognizing the underlying linear structure. The exam tests your ability to identify algebraic properties before you start writing. To prove this, we are going to break down exactly how to solve a parametric system and an adjoint puzzle, step by step. When you trust the geometry of the matrix instead of trying to brute force the algebra, you buy back the time you need to actually finish the test. Let's start with the parametric system from earlier. We need to determine how different values of the parameter a dictate whether the system has no solution, a unique solution, or infinitely many. The immediate first step is to strip away the algebra. We extract the numerical coefficients of x, y, and z and map them into an augmented matrix. Once the numbers are isolated, our single objective is to perform row operations to reach row echelon form. This structure exposes the pivots, which act as the load-bearing columns of our linear system. To clear the first column, we multiply row 1 by -2 and add it to row 2. Then we subtract row 1 from row 3, leaving zeros below our pivot. The problem now hinges on this bottom row. The upper rows are entirely stable, but this final row contains all the volatility of the parameter a. We start by testing for an inconsistent system, one with no solution. Geometrically, this happens when parallel planes never intersect. Algebraically, it manifests as a logical impossibility, like 0 equaling a non-zero number. Looking at our bottom row, we force the left side to equal 0, while keeping the right side non-zero. That sets up two simultaneous conditions, a squared minus 4 equals 0, and a minus 2 not equal 0. Solving the first equation gives us a equals 2 or a equals -2. But our second condition dictates that a cannot be 2. Therefore, if a equals -2, the row reads 0 equals -4. The system breaks, and there are no solutions. Next, we look for infinitely many solutions. This requires a free variable, which occurs when two equations are essentially duplicates. In matrix form, an entire row cancels out to 0 equals 0. We apply that rule by setting both the coefficient and augmented parts equal to 0. The only value satisfying both is a equals 2. The third column completely loses its pivot. Without a leading entry, z becomes a free variable, generating an infinite number of valid coordinates along a line. Finally, there is the case of a unique solution. For a system to define a single, distinct point in space, every single column must secure a pivot. This means the coefficient in our third column cannot be 0. A squared minus 4 cannot equal 0, which simply means a can be any real number except 2 or -2. The parameter a functions as a dial. Adjusting its value shifts the matrix between these three strict geometric states based on where the pivots land. That brings us to the second major exam hazard. Look at question 1c here on this page, asking for the determinant of the adjoint of a. Calculating the full adjoint matrix for a determinant question will exhaust your allotted time. The problem asks for the property, not the matrix itself. Instead, rely on the foundational identity linking these properties. Matrix A multiplied by the adjoint of A equals the determinant of A times the identity matrix. We derive the relationship by taking the determinant of both sides. The left side splits cleanly. On the right, the determinant of A is a scalar, so pulling it out of an n by n matrix raises it to the power of n. Divide both sides by the determinant of A to isolate the resulting formula. The determinant of an adjoint is the determinant of the original matrix raised to the power of n-1. Returning to the exam paper, we see the student apply this exact logic. They already know the determinant of A is -10, and it's a 3x3 matrix. -10 squared is 100. A 10-minute calculation becomes a 10-second mental exercise. Professors will also test this conceptually, without providing a matrix to calculate. Question 6b asks if a 3 by 3 matrix B with a determinant of -10 can be the adjoint of any matrix. Using the formula we just proved, we know the determinant of an adjoint for a 3 by 3 matrix is the original determinant squared. Any real number squared is positive. Since matrix B has a negative determinant, it mathematically cannot be an adjoint. Knowing the proof of the identity, rather than just blindly memorizing the final formula, provides the deductive reasoning needed to navigate these conceptual puzzles. On the exam page, specific patterns dictate your strategy. Seeing a variable like k or a buried inside a system of equations is the first signal. Your immediate reflex must be to abandon algebraic substitution, construct an augmented matrix, and relentlessly hunt for the row echelon form to expose the pivots. The second signal is seeing the adjoint notation inside determinant brackets. Refuse to calculate the matrix by hand. Immediately deploy the exponent property. University math exams prioritize pattern recognition and the selection of structural tools over arithmetic endurance. By isolating the pivots in parametric systems and knowing the core determinant identities, the most intimidating questions on the paper become entirely predictable puzzles. Step back from the arithmetic, trust the linear structure, and you will have the time you need to pass the exam.